The other two thermodynamic process is an isothermal change, which means temperature does not change, and adiabatic change, in which there is no heat flow allowed to go in the system. Okay, so for isothermal, again, we will see a curve. So let's say I start at this position here and end at this position. We will then see a curved graph as it goes down there. Okay, so isothermal means that the change in internal energy has to equal 0. So that means the absolute value of Q must equal the absolute value of W. The heat flow quantity must equal the quantity of work done. Okay, now we can't calculate directly then the heat flow. We need to figure out the pressure volume work for this. Now that's done by integral calculus. The work is equal to N RT natural log of volume initial divided by volume final. Now I've written the equation this way in order to always get the proper sign for work in this case. So if the volume expands, then volume final is larger than volume initial. You'll end up with a negative when you do the natural logarithm of that. And then of course vice versa. So because heat flow is equal to work, once you know the amount of work done, then you know the heat flow will be equal and opposite to that. Now in this case, temperature is equal to a constant. It does not change. Now this is Boyle's law. Pressure 1, volume 1 equals pressure 2, volume 2. So again, I hope that helps you understand that a little bit better. And then last we have the adiabatic change, and that means the heat flow is going to equal to 0. So if we start at position A here and end at position B down here, we're going to get a steeper curve to the graph, and that's because the pressure volume work is being done by the gas and no heat's flowing in to help it out. So the work done in this case is equal to the change in internal energy. So delta U is equal to the work done. Okay, so how do we calculate that? Well, we know that the change in internal energy does depend on temperature change. So we're going to say delta U is equal to N, number of moles, 3/2 R, okay, times the change in temperature. So one more time, the change in internal energy, okay, does depend on the temperature change. So whatever we get for delta U in this case must equal the work done. We could also write delta U equal to N C sub V delta T. C sub V is the molar heat capacity, okay, for a monatomic gas. Remember, there's only 3 degrees of freedom of motion for a monatomic gas, where there's 5 for a diatomic gas. So if this was a diatomic gas, that would be N 5/2 R instead. Now what law is this one? This one's the combined gas law. Pressure 1, volume 1, temperature 2 is equal to pressure 2, volume 2, temperature 1. Because both pressure, or actually all pressure, temperature, and volume are changing in an adiabatic change. And one more time, the work is being done by the gas. That's why we see a much steeper curve, and heat flow is not allowed to come in and help out.